I'm so glad to have this chance to share my opinion about the softwares and the engineering. I'm actually working for engineering, so you may think why that guy is coming here talking in the computer or computing colloquium. I'm working for the safety critical industry, especially for the nuclear. Sometimes I work for the railway risk assessment things, transportation systems. So I can say I'm a heavy user of the software or computer applications. And I feel very close to the computer science because I'm actually a dad of 2 computer kids. My son, the first one is doing his PhD at IPI for the computer science. Second one is graduating and will join to PhD program soon. And the third one is a little bit different. She's not on this kind of science. So yeah, I have two computer kids. So I feel very familiar with computer science because I used to use this kind of calculations by using the computer for all my professional career. So because you know, who want to do some experiment with nuclear power plant for accident cases? Who wanted to do experiment with missile launch systems, right? Nobody want to do that. Then how do we know that nuclear power plant will be okay? Or how do you know that if you push this button, this missile will launch, right, to the place where it is supposed to go? So all the computer simulations. So that was conventional, like old time story. So we calculate, simulate something, very much of details. So that's not a main issue anymore in these days. That's quite much of daily life issue. So we know that this computer system will give you the correct answer when you want to see it. How we gonna use it, or how we can extract information from that computer simulation. And sometimes we use computer for very critical issues like when accident comes to the nuclear power plant, we need to treat the reactor, right? That will be automated. How do you know that computer system will do its job, right? With like 99.99% of confidence. And if we drive Tesla, in this day, Tesla didn't actually launch their former version of autonomous, right, driving system. It is, they always call it a beta version, right? Because they don't want to take a responsibility from the accident. But that kind of autopilot or autonomous driving, how do you know that your software will not make an error? Right? What is acceptable? What is acceptable? Acceptable uncertainty we can afford. So all that kind of issues are the current issues. So I will go through those topics one by one. So because I'm working on safety critical issues, always safety matters. So we should make a scientific decision under uncertainty. We will not rely on gut feeling, right? We should go here. We don't do that. We need to make a scientific decision making. How we do that? How we capture that uncertainties. And then we will talk about a little bit about simulations as a vehicle of exploring various scenarios. I use very gentle and nice terminology, various here. What I mean is extreme cases. We really don't want to have it here. Then we will use computer systems, and that's quite much known in these days. And a systematic framework for the model-based decision-making will be the following options. So we have plenty of data produced by computer systems. Without computer, in like 20, 30 years ago, if we, at that time, we heavily relied on the experiments. How many experimental cases you expect to have when you make a decision? Like maximum 10, 20, each of experiment, if it is related to the safety or very heavy systems, it will cost $1 million. So if you have 100 cases, means $100 million you spent for that experiment. That's it. You cannot expect any more. But in these days, because we are using computer systems, you're gonna have really huge amount of data. How you extract useful information from that? That's another question. So I just wanted to introduce what my students and myself is doing in this area. And then last topic I want to share with you is a little bit different. Verification or validation of the software algorithm. So we automated. When we automated something, this is really important. So how we guarantee that this software will do what it's supposed to do, right? So I will show you one by one later. Before that, I just want to show this slide about my organization, my institute. This is RPI. I got this picture from Wikipedia, so I don't know whether this is truly that old picture, but it was, I mean, RPI, Rensselaer Polytechnic Institute, was founded 1824, so it is almost 200 years ago. And next year, it will be the 200 year. So this one is the oldest educational organization which started giving engineering degree. So we can say, but some people say that this is oldest engineering college in English-speaking world. Yeah, I think some Italian or European universities did it before the RPI, but this is actually the first one in this country. And I want to start my talk today with this slide. So this is about the viewpoint. When you look at this first picture, you see this baby and father, right? And compare it with this picture. This gentleman and lady is doing something like bungee jump, right? And this staff is professional here working for this bungee jump facility. Look at the face, the baby's face, and compare it with the faces of these two. And you see, do you think this father is really expert of this kind of play? What is the probability that he failed to catch him back? You think this? He is professional, right? He's doing this for his life, daily living. And you see the equipment here, right? What is the probability that this equipment fails to catch them before they crash on the ground? If you compare that, you see which one is riskier. Scientifically, you know that, you know answer, right? This one is much more safer than this one. You have multiple ropes installed in your body, and this professional is checking everything again and again. This one, he's really amateur, right? This must be his first time to toss his baby like this. The probability is really high here, right? Catastrophic event. But they do, and they are laughing like this. So this is the difference. So we don't do decision making based on gut feeling like this. It should be calculated and scientific. It should have scientific basis. So that can be connected to this slide. This is typical. You know, yeah. This is for elementary school, right? So if you toss the coin half and half, we all know this, right? If you toss the coin in the vacuum chamber with a very accurate machine, and you know the mass of the coin, you know the initial angle and the force of toss, everything, do you still think this is half and half? No, you guys can calculate, right? Which side will up? And then it's almost deterministic. It's not probabilistic anymore. If you know everything, no uncertainty, then it is deterministic. So in the vacuum chamber, no wind, no friction, everything is known and you can calculate it. Then this is deterministic. This coin toss is normal half and half game, right? And this coin toss half and half, because you don't know, there are so many uncertainty factors involved. So in this case, we use probability to capture this associated uncertainty. But for this, we don't have to. That's the role of the probability in the uncertainty management. So when we talk about a little bit uncertain event, we usually say that the probability that this car cannot stop within this distance in a snow day will be like 50%, will be 40%. In that way we express, right? That's how we capture the uncertainty by using the concept of probability. And this is an example of that probability calculation. This is Korean Peninsula. As Hoda introduced, I'm from Korea. So this project was asked by Korean government. They wanted to calculate the risk of maritime transportation of something very important from here to there or somewhere to the other place. So that transportation pathway, because this is sea, right? This is not a road system. So you can make a different pathway to go to the specified destination. Then what is the associated risk of this transportation? They wanted to know. Frankly, it was for the spent fuel of nuclear power plant. So spent fuel is radioactive. If there is a serious accident, then they may have sunken ship, right, with radioactive material. And then it will be like, really, difficult case, right? So the government will be in a difficult situation. So they don't want to have that issue. So wanted to know the risk. Okay, this is actual request we engineers will have. And then we don't do the experiment, right? So what we did was calculating risk, associated risk by using computer simulations. So in our case, first step was developing this kind of event tree, which expresses possible cases. So collision happens, and then what kind of collision, where it happened, and whether the collision was strong enough to destroy inside of the ship structure, or collision will be strong enough to destroy the cask inside, something like that. We will develop this kind of event tree. But we don't know the branch probabilities here. So branch probability should be calculated separately. So this is the, I don't want to go into too much of detail because I don't think you have much interest at maritime transportation risk calculation. I'm using this just an example of conventional calculations we do in safety critical engineering field. So then we will go for maths, right? So the probability of collision will be calculated by geometrical chance of encountering another ship, and then probability of evasion failure. So those two will communicate to avoid collision. But if it fails, they will make a collision and will be an event, right? So how do we calculate probability of encounters? So what we did was by utilizing so-called AIS data. It is the position data of the ship. So the ship is supposed to send their position data to the control center periodically. So we obtained that data and do some computer calculations and develop these route intersections for each time step. Right? At daytime, we will have much more traffic. Nighttime, we will have less traffic. something like that, so that it depends on time, but we're gonna have this kind of average route intersection like this. Then if my ship is going through these intersections, then now you will be able to calculate chance of meeting another ship, right? At a certain port, this is very one of the biggest port in the world. So this is very popular. I mean, the dense traffic here nearby. But on the other side, we don't have much traffic. So the risk of encountering another ship will be small. And when you meet a small, like a fishing ship, when you run a huge nuclear spent fuel transportation ship, small fishing boat doesn't care, right? They may be damaged, but they will not damage on this ship. But if you encounter oil tanker or huge container ship, that's totally different story. So you need to think about all that kind of, how can I say, population of ships, right? And then do some math. Of course, you cannot do that with paper and pencil, so we're gonna use computer. And then once a collision happens, then what we should know? We want to know the probability of damage. So actual damage on the spent fuel. So something important inside. So we will learn this kind of simulation. This is simulation 2. This is a finite element method, FEM simulations, to see how much of damage the other ship will make. It depends on the angle of collision and the shape of the ship and the strength of the structural material inside. So this is, again, uncertainty. We should have profile of different cases, and we learn million simulations to see what is the profile of the damage. Then we will be able to calculate risk like this. So we use risk as a metric of the decision. So if high risk, we don't do that. If risk is low, we prefer to take that route. So different cases, you will be able to calculate this risk. This risk is radiation exposure per transportation. So possible radiation exposure we calculated like that. And one interesting thing is like this in this simulation. If we have fast ship travel, then when accident happens, the consequence will be larger because it was fast, right? The impact will be stronger. But that fast travel will reduce chance of encountering another ship. So which one is more important? Based on our calculation, faster is better. So that's what we suggested at that time. But yeah, this is typical procedure of calculation in previous years. When demand comes, then we analyze the situation. Engineers usually, how we approach it, how we divide all the situations systematically, and how we calculate this. We will choose proper options for each case, and we run the simulations. And that was like old story. Like it was done like more than 10 years ago, and at that time that was good use of computer for engineering purpose. In these days, that's different story. I got this picture from medical area, from medical journal regarding COVID-19 simulation at the beginning of that pandemic situation. My question is, what do you see from this result? All possible trajectories computer simulation created. What do you see? If you are a decision maker, how do you use this data for your decision making? What information you can extract? That's challenge now, right? So the creating data is now, easy. I don't say easy, but it's doable, right? So, and we have plenty of computing power. So we have huge amount of data. What does that mean? What information we extract? This is another story, but Idaho National Lab here nearby, not very close, but your neighbor here. That Idaho National Lab is the organization which is leading a new trial, dynamic risk assessment. So risk was calculated in conventionally like a static value, 10 to the minus 6 damage per year, something like that. So if you keep running this plant for million years, you're gonna have 1 damage, something like that. But situation is different, case by case. So in order to capture that variety of risk, they use so-called dynamic risk assessment. One of the biggest, so they, the National Lab's computational capability, right? They produce really huge amount of data of nuclear power plant operational profile. And then how do you extract risk factors from them? Which one is actual risk? How do you use it for real, decision-making support? So that was big question. And what I wanted to share today is one possible approach. I don't say this is the best, but this is what we are doing. My students and myself, my team is doing this systematic approach. This one possible way of that. First concern was how we convert actual design to the physically meaningful causality map. Right? So, and then this causality map, how we can convert it to the state space. It's a typical computational world, right? So if you just convert this real world design into the state space, a lot of subjectivity. That's a big issue. So it depends on analyst. Somebody will create this space, the other will create different one. They cannot communicate each other. And especially when that information is provided to the decision maker, like in the nuclear power plant main control room, there are operators. Operators do not understand what this machine is talking, right? What operation they are asking for me. And that's the problem. So that all that state space needs to have its own physical meaning. Otherwise, we cannot communicate with human decision makers. So what we thought was converting this physical system into the causality map by using a so-called multi-level flow model technique. And then we will just convert it mechanically to this Bayesian network model. And we will make a decision based on Markov decision process. So I will not go into details of this, but this is the suggestion we made. And the intention is keeping the physical causality while we minimize the subjectivity involved. And then we have another question. When we have state space mapping like this, how we determine that space for each? Right? So if we have this rough cells, then the computational load must be small, but we don't have resolution. So we cannot distinguish this group from the other. If we have this fine cell, that's good. We will have better resolution, but it will require a huge amount of computational power. How we optimize it is another story. So what we did in our case, because we are talking about physical plant, first step was using the physics knowledge. So like this line is for dividing gas from the liquid, right? When you heat water, it becomes steam, but when pressure is high, it still must be liquid, something like that. That kind of physical knowledge will be used at the first step. And the second step, we will consider component state. Something like, oh, that valve was opened, so it becomes like that. and the motor was working, pump was working, then it will be different. So this color coding means different component state. That's also physical knowledge. And then we will be able to create these small groups by using machine learning based clustering something. This is good, but we are not very happy because all other spaces are not covered. When we have data here, what does that mean? So that's the problem. So what we used was using support vector machine to make a space divided like this, so it will cover whole possible space. Right? So it is kind of combination of physical knowledge with machine learning or data analytic approach. And then I don't usually share this slide when I give a talk because people really hate this kind of complicated mathematical equations. But I'm now talking in computer colloquium, so I believe you guys love this kind of equation. So all that uncertainties analyzed, and then we will have this conditional probability equations. So our goal is solving this equation and finding best option. We go, right? So yeah, this is, and well, one more important thing is sometimes it is, as I told you, when we don't have information, it is what? Uncertain. So we use probability. But we have information, that's different story. When we don't have information about this pump, because it was in operation for like 3 months, keep working, its failure probability will be like 2%, something like that. That's what I estimate, right? But if we have measurement at that pump and measuring the vibration and everything, then you will make different decision. Not 2% anymore. Like, it is dying. Right? The failure probability tomorrow will be 99%. Or it doesn't have any vibration, everything goes well. What I mean, if you monitor the current used by this pump, everything is very smooth, then still, well, like very new one, right? 100% of reliability, something like that. So if you measure something, your decision must be different. So that kind of measurements will be reflected at this conditional probability equation. So then we will be able to solve it. And this is an example. You see all different abbreviations here, but this is for the sodium-cooled fast reactor. So we developed this Modelica simulation toolkit. In these days, it's so easy, right? It must be a huge project. Developing this simulation itself was a huge project in like 10 years ago or something. But in these days, so I mean, it will take just several months, something like that. And we developed this simulation toolkit and learned it a million times. And we have this state space model here, and we calculated all the conditional probabilities, right? And then decision making can be made based on the information of component status and possibility or the probability of trajectory. So we will be able to make a scientific decision making. So if you choose this option, then you will have like 99.5% of success and 0.5% of failure. If you choose this option, then you're gonna have 20% of failure, 80% of success, something like that. And sometimes there are very complicated reward schemes, right? And let's go back to the nuclear power plant option. Then, if you keep running it, you will make money, right? Because you can sell the electricity and you will make money. But if you make an accident because of that operation, you may need to pay like $1 billion. Right? So then, what you should do? How we make a better decision? So that kind of decision can be made based on this mathematical expression. This is just for illustration purpose. It couldn't be that easy, right? the decision-making space is huge, but it's just for illustration purpose. Yeah, that is the one example, or I can say this is one possible approach you can make for handling that complex or huge data sets. The other issue is, this is a little bit different view, right? And what I explained was very complicated simulation, plant behavior, something we have information, then what is our expectation, something like that. Here, I'm talking about different story. If you automate something, what is the reliability of that software, I mean, automation software? What will be the effect of the software failure? I have some extreme case example here. One of the nuclear power plant equipped with 16 redundant computers for calculating safety parameters, because they don't feel comfortable, right? If you have just 2 computers here, in daily life, 2 computers in parallel is good enough, right? If this fails, the other is fine. Yeah, they increased it to 4 channels and voting, right? And then they don't feel comfortable. So each channel has 4 different calculations and redundant. They are comparing each other. So in total, 16 redundancy they have. Stupidly, they use exactly same software there. So if there is any software failure, you will lose 16 redundancy at the same time. What we calculated was, let me share this information first. This is typical safety critical world, and you know the price of each software piece in this industry. This you don't know this. Each piece will cost multi-million dollars. It's just, I mean, 200 lines only, or sometimes it is like several thousand lines. Well, you guys can make it in one night. You don't work during daytime, so I count nights. So you can develop it in one night, but you can charge $1 million because it should be verified in multiple years. So that's a little bit different story. But even after that expensive computer, this is a reported case in nuclear industry regarding the digitalized system. I'm not talking about the mechanical pump valves things, but this is about the digitalized system. Software error was 30. And computer random failure or electromagnetic interference things like this. So among 79 cases, 30 was about the software. One very strange experience I got was the computer which calculates consumption of nuclear fuel. That's important, right? Important calculation. The computer that halted periodically, it must be rebooted. Otherwise, you will have a wrong number of that fuel consumption. Then you will choose different operation option. That will be big trouble. So they, frequently reboot their system. That kind of issue belongs to the software error. Right? If you reboot it, you can resolve it. But so, and then how important that software is. This is the calculation we made for the reactor protection system. So reactor protection system function is so simple. When something happens, you will tip the reactor. Well, pressure high, tip the reactor. Temperature high, tip the reactor. So easy, straightforward. But if it fails, what happens? So when software failure probability 10 to the minus 6, this safety system failure probability is like this. But when it increases 10 to the minus 5, a little bit of increase. But if it goes 10 to the minus 4, then it will make 25% increase of system failure probability. It goes 10 to the minus 3. Oh, then software is dominant. You know that in general, safety critical equipment like pump valves, reliability is around, failure probability is around 10 to the minus 3. So even 10 to the minus 4 software makes 25% increase of system unavailability. This is critical. So we wanted to make sure this software doesn't have an issue. And I told you, same version of software will be used for multiple redundancy of hardware. So safety of the software is critical. So we wanted to verify this software is fine. And if we go inside of that plant, what you see is, this is what you see in the control room. But behind this control room, you will see cabinets like this. So these are the industry computers. Unlike the servers, modern servers or the personal computers here, industry computers are like this because they need to have cooling system separately, and all these modules will be managed separately. But this is actually a computer. It has microprocessor inside. It will calculate something based on the input and make an output like that. And we want to make sure this is okay. I'm talking about the nuclear power plant protection system here, but it is quite much same to the Tesla's autonomous driving system or other autonomous unmanned vehicle systems. Quite much same. How are we so sure that this software will be okay? So what we tried was, this project was funded by a utility company. So they really wanted to know what is the chance of failure of their safety critical software. So what I suggested was like this. We will divide system into 3 pieces. One is hardware. This is supposed to experience what? Random failure. And the other is operating system. It will encounter various operational issues during operation, right? So they will experience more uncertainty. Here, application software in this safety critical system, it is unlike this Microsoft Word or Windows systems or Apple's operating system. In this system, this operating system is so simple and straightforward. And once this high priority software kicked in, nobody can interrupt it. It will finish its work. And then the queue will be returned to the operating system. So this application software execution will be almost guaranteed, right? And this application software, once kicked in, then it will just execute from the first line of machine language, right? Machine code. First instruction to the last instruction. And we will minimize branches or something complicated calculation for this kind of safety critical software. We will just have straightforward calculation. How do we handle it is different. So if temperature is high, when you guys make software programming, we use branch, right? If this is high, then you will go for this calculation. If this is low, then you will go for different situation. Here, this is safety critical software. We don't do like that. We will just calculate set point minus measured point, right? And it will be stored somewhere. So if it is negative number, will be used negative sign in the next calculation. Positive sign, if it is positive sign, it will be used in the next calculation as positive. So it will not make a branch. It will just follow step-by-step calculations, right? So what we aim to do was proving this application software error-free. That's the only option we can see, right? By testing, there are a lot of problems. I will explain here. Yeah, this is actual experiments done at Idaho National Lab and Brookhaven National Lab. I was involved in this project. So what they did was for actually the same thing. Reactor safety system, nuclear reactor safety system, Idaho National Lab has. And Brookhaven want to prove how safe it is. They learned just they were able to run 10,000 cases only, because in order to check whether this safety system is working well, what we do is feeding a scenario and check whether output is correct. Feeding a scenario and check it. That takes time. Creating input takes time. Run the simulation and finding the output takes time. So it will take several minutes for each testing. 10,000 tests is good number. They made like that. So what we thought is, even they did 10,000 tests, they are still, they had difficult time to answering all the questions. Like, are you sure that you test all the coverages, all possible cases? How are you so sure that it's randomly selected? You may just select input from this area only and the other area never tested. Then do you really use this test result as a basis of this software safety? That's really difficult questions. And when we talk about scenario, that's time dependent, right? How long the scenario must be? I used 1 hour scenario. Not enough. You may need to run it for 1 day scenario or 1 month scenario for each test. Then you will be in real trouble. So that's the, even with this number of tests, they were not able to specify the reliability of this software. So what I thought was, okay, we will not go for the scenario-based test. So we will just think about input space. So in the digital world, what is infinite? Nothing can be infinite. Everything will be presented by 1 and zeros, right? So even analog numbers will be presented by like 16 digit or binary code or 32, something like that, right? We have a limited resolution. That's big number, but not infinite. So we can handle it. So what we want to do is doing computer-based testing, simulation, emulation-based testing, make it very, very fast. Our target was millisecond for each test. Then we can cover billion cases. And that's what I thought. So we wanted to demonstrate that exhaustive testing is doable. And this is what we did. So we developed, first step was emulator of the computer. Sounds very tough work. Yeah, tough, but it's not undoable. So we specified CPU registers and memory areas, actual system use, and microprocessor I didn't specify here. Somewhere else you will find the number, that microprocessor. So for specific microprocessor, which was used for that specific computer protection system. So we emulate everything, and we also emulate, here, this is specific microprocessor name, was produced by Texas Instrument. And we also emulate what this CPU is doing, something like instructions, right? If this instruction is add 2 register numbers and store it somewhere, right? We will just do that, right, without hardware. So we just made that software packages for that. So we call it in-house emulator of the computer system, industry computer systems. And you can see each combination of inputs and internal variables makes one test case. We change it, the scope or the view of testing. It used to be trajectory-based testing. Now we are moving to input space or input domain-based testing. We will cover all possible input domain, all possible combinations, not only the input, but also the internal variables, stored memory should be considered. So each combination will make one test. Required number of tests will be multi-billion, right? So that's what we did. And as I told you, nothing infinite, and analog inputs will be converted into the limited number of bits. And under this circumstance, we can make automated testing. So we don't have to feed the scenario and check it manually like that. So we will make everything automated because all the computerized here, right? So this is test executor, and it feeds test input. So it will store the test values at the specific memory and the register and input variable and learn this emulator. And this emulator will execute what machine instruction from the first line to the last line, and then return the result and check it whether it is correct. So that's what we did like this. And then you should have that exhaustive test cases. That's another question. If you just open to every possible variety of the variables input and stored values, then it will be really huge, not the, yeah. So what we wanted to do was, this is safety system, right? Its function is what? Trip the vector when something goes wrong, right? So what we wanted to test was the what? Trip range variables only. When it comes to trip, whether this software failed to generate trip, that's the concern. When it doesn't have to be tripped, it creates trip signal, that's fine, we don't care. That's not a, safety issue, right? That's an issue, that's a malfunction of software, but we don't care, it's not a safety issue. Safety issue happens only when demand comes, but this software failed to create trip signal, right? So we will focus on that conditional cases. Then we were able to reduce the space into like 100s, 110s, something like that, much smaller. There are multiple ways to create that exhaustive test cases, but in this slide, because you guys are computer guys, I picked this SMT solver-based case development, but you can create it different ways. So SMT solver is good for computer guys, but nuclear regulators, they don't want to see that SMT solver things. So in that case, we should have something traceable. So we also developed fault tree-based test case creation something, but I will not explain about it here today. So how many minutes do I have? Yeah. So this is SMT solver-based test case generation scheme. Right, so we will create first set which satisfied requirement, and then go for the next second set something. Then until we cannot find any solution, we will do repeat this search, and we create huge database for the exhaustive testing. And yeah, this is the case. I don't know why my student took picture with these post-its over the computers, but that's a computer guy, engineers do something like that. By the way, so I don't have to explain all the details of the function, but in general, I can say the number of test cases we created was here, like how many zeros? Million, billion. 134 billion, right? So original space was something like trillion, but we were able to reduce this something like a billion scale here. Why? Because it was fully computerized, automated. Each test took just 3 milliseconds only. For the first instruction set to the last one, make one full execution of that application software and checking the correctness of output will take just 3 milliseconds. What I did was actually, frankly, I wanted to use a supercomputer of RPI. Believe it or not, RPI supercomputer is the best in private university in this country. So I wanted to use it, but they didn't allow me to install this kind of software we developed. because they worry about my software may damage their system. So it takes time to verify this is okay. What I did was, I was paid a good amount of money. So what we did was we buy just high performance computer, 10 sets of high performance computer. Was like a Ryzen microprocessor. It equipped with, you know, that 32 cores inside, and each core will create 2 calculation threads. So 64 calculations at the same time. I bought 10 sets, right? Then I have multiple of what, 640. And all this test run took like several days, right? So not many years. If we think like scenario-based testing, if we accelerate it successfully, each test like 10 minutes for each test. And we want to demonstrate this is 10 to the minus 6 failure probability. Then what you usually supposed to do is, even you can guarantee a random selection of input profile, it will require like 3 million tests without failure. Then you can say with 90% of confidence, 10 to the minus 6 failure probability. So this is very general rule of simple calculation in the statistics. So in that case, 10 minutes means you can run 6 tests only per hour. And you need to run 3 million case tests. It will take like 60 years or something like that if you use one testing set. If you make but you know that test set requires a simulation toolkit and actual software, and it's running hardware platform. It's costly. So even you install multiple lines, it will be like 1 year just for testing. So in this case, by for 10 computer systems like this here, and run it for several days, and you prove that this software does not create any safety issue. And what we did was using actual reactor protection system executable, because it was funded by a utility company. They are a big customer of that reactor protection software developer. So they provided us executable. They didn't share the source code, but executable. So that executable was actually done from the first line to the last line, repeated multi-billion times like that, and we demonstrated this is error-free. I think it is the first case in this industry, but this is what I thought about the verification, validation of software world. But this is for the very straightforward system, right? When it is very complicated, test case required number of tests must be much larger, right? Like Tesla, autonomous driving. How many tests we should run for proving that this is good, right? But I think this is certainly important for many other issues, like in these days, even nuclear engineering, we are considering autonomous operational plant. There are 2 reasons. One is because that human is the source of trouble. Always human caused the trouble, right? So I told you who wanted to run the test with actual nuclear power plant. Somebody did. It was Chernobyl. And in the TMI accident in this country, it was also caused by human error. Human. So we just want to remove human from the plant for the better safety. In that case, autonomous operation of nuclear power plant. What do you think? You feel comfortable with operate autonomous nuclear power plant nearby your house? So that's the question. How are we gonna prove this is okay, acceptable, right? What portion we missed? And So what I wanted to share with you was not the details of these technical issues, but the issues are changing. It doesn't go further. Okay. So this slide summarizes what I talked this morning. So many safety critical engineering problems are addressed based on computer simulations. So that's simply equation solver. When we can express some certain problem with differential equations or logical equations or whatever equation, then computer will solve that equation. And we run the simulation and data produced. Abundance of data will make a headache. And then data processing is important. And how we're gonna use that for decision support is different issues. So human factors and computer, human-computer interface will be involved there. And when it is safety critical automation, the testing becomes crucial. Actually, in the nuclear field, you know, the regulatory body is huge. So that regulatory body was very nervous on the use of digital system for the safety critical functions. Yeah, or everywhere else was already digitalized, right? In the nuclear, they are still struggling, fighting with the regulator. Please accept this computer-based protection system. And then regulator always says, show me, it is good enough. Right? So because you know the characteristic of digital computer systems, when it fails, it is all of a sudden, right? Your computer, when it be hurted, right? When you see the blue screen, it doesn't give you warning, right? It just to show you the blue screen, that's it. That's a non-linear characteristic of computer behavior makes a regulator very nervous. And they wanted to see the proof. So classically, they rely on the test, right? So what I suggested was something about it. So automation, if it is safety actions, like autonomous driving, safety action means braking, right? If the car doesn't stop when it should, what happened? You're gonna die or somebody will die, right? So it should be checked. And input domain is not infinite, so we talked about the exhaustive testing, but when it is really complex, how are we gonna talk about test, right? So we should be more wise. I mean, like we should tailor the safety critical action out from normal operation. Like when we talk about autonomous operation, autonomous driving of Tesla, then we will just talk about braking, okay? We find something, whether this braking signal will be created or not. That's the question. And we're gonna test it. Something like that. We should be more, more sophisticated at this kind of testing procedure development. Right? And data analytics is a really big issue in these days. Not in only safety critical engineering, but safety critical engineering is the area which got benefited most from the development of softwares and computer systems. Before that, doing safety-related experiment is really, costly. I remember when Korean government decided to build a small, miniature-like safety experimental facility. There was a huge debate. Do we need to pay $1 billion just for the testing facility? It will not create anything new. We just want to verify this concept is correct. It does not show us the other design is better. Well, because the other design was never been implemented. Another implementation will cost you another $1 billion. It was a huge debate. In these days, we don't build that test facility anymore. So in US government funded a lot for that computer-based simulations. So the first, for the single phase, like water-based reactor, we don't need to have experiment anymore. So the calculation is almost correct. multi-phase, something like water boiling and something, then we have a little bit of uncertainty still, but almost there. So we can say that producing data is quite much doable. Now, how are we gonna handle it? How we talk about this whole spectrum of world? Because at all the time we didn't know that kind of thing may happen. So we didn't have to talk about it. But now that computer reveals everything, so there is some corners never been visited. So we are in a different situation. So that's the last bullet I wanted to emphasize. So data analytics plays so important and critical role here. Yeah, that's it. Thank you so much.